All right, welcome everyone. Let's get started with some questions about the homework. So this is homework 7, which is due tomorrow. Yep, today's Thursday. Problem 2. So Allison asked about problem 2D. So the p-value is the proportion of samples with the value of x bar what? So this was using the haircut costs data set. There it is. Not to be confused with the haircut prices data set. So we're just going to do Control A to highlight all, and then Control C to copy. And then we'll go back to the one mean applet. Clear out the existing data and Control V to paste in the new data, and then use data. And here we have a sample mean of 45.68. Make a note of that. And we were testing I think that was on the previous problem. Whether the average price of haircuts for students in the class that this data was taken from is different from $43. So our alternative hypothesis is that mu does not equal 43. So that means that in our applet, we want to apply a mean shift to get the mean of the population to be equal to 43. Oh, and I'll go ahead and select the times 40 button to increase the population size. And then we'll apply a mean shift until the mean of the population is 43. And I'm using the arrow keys to get small adjustments there. So the mean shift that we needed here was negative 2.68. That's because the difference between 43, that was the hypothesized value, and the sample mean, which was 45.68, the difference between those is 2.68. All right, so then we're ready to do our simulations. So let's go ahead and do 1,000 samples. And what was the original sample size? Meh. 50. So I need to reapply. There we go. So sample size of 50. And draw samples. All right. So the p-value is going to be the proportion of samples that were at least as extreme as what we got in the data. So what we got in the data was a sample mean of 45.68. And we want to count the samples that are at least as extreme as that, where what counts as at least as extreme is based on the alternative hypothesis. So we had a two-sided alternative hypothesis here. We were testing whether the mean was different from 43, not just whether it was greater than. So we're going to change this to beyond or equal to 45.68. So here I'm getting a p-value of 0.597. Your value might be slightly different from mine because you got different random numbers. But a key thing about this problem is to notice that it's not asking you what is the p-value. So it's not asking you for the 0.597. Instead, it's asking you, how do we compute the p-value? It's the proportion of samples with the value of x bar beyond or equal to the sample mean, so 45.68. Questions about that one? Allison, does that address your question about that one? Mm-hmm. Cool. Other questions about the homework? Fine. 8, A, B, and C. Okay. Oh, good. So in a certain population of adults, the mean salary is 29,321, and the standard deviation of salary is 18,562. You take a random sample of 100 adults from this population and graph their salaries. So in other words, this is saying, if we made a dot plot, so each dot in this graph that we're talking about right now is the salary of one person. So I'm going to skip over part A and come back to it. So the mean of the individual observations, so the average of this graph, is most likely close to the mean of the population. That's kind of the whole point, is trying to learn about the population by taking a sample. That the mean of the sample, the individual data points in that sample, is probably close to the mean of the population. And then the part C, the standard deviation of the individual observations. This is tricky because you need to look at which standard deviation it's asking about. So this is saying the standard deviation of the individual observations. So in other words, taking these 100 values and just finding their sample standard deviation. That's most likely close to the standard deviation of the population. So that's most likely close to 18,562. That's different from part C. So here, each person in our statistics class takes a random sample of 100 adults and finds the mean salary in their sample. That's talking about each one of us finds 100 people and takes their average salary. In that case, each of these dots is no longer the salary of one person. It's now the mean salary of 100 people. So in this case, when you're finding the standard deviation of the means, that's when the standard deviation decreases. That's when you take the population standard deviation and divide it by the square root of the sample size. So for part, no, I just realized I had two parts, A, B, and C. Sorry about that. That should be D, E, and F. So for this last part, the standard deviation of the sample means, this is when we're taking our 18,562 and dividing it by the square root of 100, which is 10. So we end up with about 1,856.20. Questions about the mean and standard deviation before we talk about the shape? Okay, so the shape of the distribution. We know that the distribution of the sample means is most likely approximately normal. So that's what you saw in the video for today, that as your sample size gets large, the distribution of the means of different samples of that same size gets approximately bell-shaped. But this one up here is tricky. So this is talking about the distribution of the individual observations, so individual people's salaries. And for that, we don't have the central limit theorem because we're not talking about the mean, we're just talking about individual people, one person at a time. So that could be approximately normal or right skewed or left skewed. But if you think about the context of the data, there are two factors here. One is that individual people's salaries can't be negative. So we have this sort of hard left-hand boundary that the salaries can't be below. But there's no particular upper boundary on people's salaries. That there are people in the world who make $1 million a year. So those people are giving us a long right tail. They're giving us outliers. That tends to make things like salary, so often things that have to do with money, that have a fixed lower boundary, those often end up being right skewed. In this problem, we have an additional piece of evidence that that's the case. And that is that the standard deviation is large compared to the mean. So the standard deviation is 18,000, the mean is 29,000. So if you think about what the empirical rule says, so here's our empirical rule, here's our mean, we'll call this 29,000. Suppose that the distribution were normal. So we could use the empirical rule. Like, let's just suppose that the answer was approximately normal. In that case, we would expect two standard deviations below the mean. We would expect 2.5% of the data to fall below two standard deviations below the mean. Agreed? All right, but two standard deviations below the mean here would be 29,000 minus 2 times 18,000. So 29 minus 36. So negative 7,000. So we would expect 2.5% of people to have salaries less than negative 7,000. But we just said that salaries can't be negative. So that's additionally telling us that we must not have an approximately normal distribution because the empirical rule doesn't fit here. Questions about this? Nettie?
We all know was talking about like baby weights. We were supposed to use like -3 for the lower bound results.
Good question.
Not 0. Why is that?
Good question. So for the baby weights problem, you are using a normal distribution as an approximation to weights. So they're like, if the problem is saying use a normal approximation, then you want the total probability under the normal distribution curve to add up to 1 or 100%. So you don't want to artificially cut it off at 0, because then your normal approximation wouldn't work correctly. So you're right, that is kind of funny to be saying there's some probability of having babies with negative weights. It does end up being pretty small with the realistic means and standard deviations. But it's a difference between that problem saying use a normal approximation and this problem saying is a normal approximation reasonable? Other questions about this? Other questions about the homework? All right, are there any questions about the videos that you watched for today? All right, just as a heads up, we do have a quiz coming up that'll be available after class on Friday to right before class on Monday. So there is a practice quiz available on Canvas here. So I recommend checking that out. You can ask questions about it in class tomorrow if you'd like. I didn't bother encoding the practice quiz as a Canvas quiz this time. Because I figured now we sort of are in the swing of things, you sort of know what to expect from the Canvas quizzes. So I just put the questions into a Word document. Sound good? All right, so let's practice with these ideas of a normal approximation and the central limit theorem. So give these problems a try and let me know your questions. And for anybody watching this recording later, this is the Normalcdf and invNorm activity.
Oh, no.
Yeah, any whole square has to be built in, so it's even cheaper. I think.
So one is the population.
You don't want that sample size to be so more. What does that do? It doesn't give us any standard deviation. That's for standard deviation.
Probably is, and you should study it like a small.
Not use it, tell us what you get.
I would say.
Oh, so one of these is the population, and two of these are the same. So you're taking the average. So we have to find out which one the population are first. And which actually that one's. So I want this one. I think there's variation in my classes and what the reference as if you want to most which is the most or the higher
So graph population is essentially taking this sample size.
so this is the population and this is and it was
Yeah. So if any of them is skewed, the
Wait,
population.
why
is
do you
gonna
think
be-
that the standard deviation is one of the?
I think we would have been the other one. This is this has this one.
Oh, no, wait, Yeah, this one's smaller.
So I think this one is the population.
If you're saying it's true, then that would be right.
Oh. I thought it was
But also, like, when we also that makes sense. This applies to what then the larger populations are. You could make it. I'm pretty sure. Pretty sure that's 100.
That's what key value is.
So we do like
It wasn't the same.
maybe
I think you're supposed to use, I'm gonna try to do the standard deviation.
Well, this one is 0.25 already. This one is going to be 1.4. Actually, no, a little more than that.
my reasons.
I'm gonna try, I'm probably,
I think C is. You see, it's got bell shaped. Which would that be? Any?
but then, yeah, so it's the whole population, so if.
Yeah, I know that, but which one has a bell shape?
Well,
This one's like the better.
Yes.
Well, I'm saying which one of these we tell.
Oh,
I can tell which one's
the
missing.
population, well, how you think about it, these are simply distributions, so that means that the population is taking figures in 130. Or 100, you know it's gonna be 300, that's just a portion.
Okay, so how big is the population?
You don't know.
What if it was like 10 and we
It
multiply
can't be
by
10.
10 to get 100? I mean, multiply by 40 in there.
No, I don't think that's, but I think this is gonna be just.
This is an explanation. That's just moving our hands forward, like just that.
Wait, we're not.
That literally-
It's like, it's 5 percent.
We're not. Don't be absolutely nothing. It's just.
No, we're not gonna multiply by 40.
No, I think the only is doing the sample, and then we have to make a big population.
Yeah, but this is.
This makes sense. The population's to be greater than
99.
that. For sure, that one is 30.
I am literally.
Okay.
So this is normal.
Oh, wait.
Standard deviation. Maybe, yeah.
Well, yeah. And then, so we do like,
Yep.
I'm gonna try like one of mine. And it doesn't.
That's what it is.
Oh, okay. So we can. Or less, so then it's 0.05. When you guys are working on this.
I think we'll do it left, right?
She said some regulators, you can choose,
So I always leave it left.
unless you want more than, unless it's more greater than, but for the process.
But if I don't.
Yeah.
So I'll keep it a little.
I mean, most of the.
I got the.
Okay. Same. What'd you say?
I got it.
Would you do?
Did you guys?
Question.
That was one.
I'm asking her, so I can go first and figure out.
Oh, okay. It's 'cause I know what it is.
Okay. There we go. All right, next.
Would you do like
50.654. If you want to round it up, that's fine.
Okay, so this is the interest rate. But she wants to get rid of that.
Inverse norm is when you already have 50%.
Yeah, she's carrying out. This one is. Like, we're trying to find.
Just anyway.
I don't know. I don't know why you're telling me that I already, I know what it is. I don't know why you're telling me.
Yeah.
At least I'm telling you something instead of making it hand.
So then this one, it's like the area, Zero five. Yeah.
Wait, what? Okay.
That's it.
Here? No, I don't know why. Oh, I don't know.
because the sample size would be small.
Yeah.
Small size.
Yes, this is what so that's why you use the 5%. Right, it's just less than 5%.
Yeah.
But what's it? 12?
Well, it's an entity of this, it's not. I don't think we would do one like that, how you
Get it?
Here, if you like, it's like this, the value.
Yes, not talking why. Sorry, so confused.
So.
Don't have it. But if I had to guess, I would say no.
This one is actually fairly similar to the cell.
I was thinking the same thing, a high standard deviation compared to the.
Using the standard deviation.
Should be that. Even when it's. Basically, it's probably skewed somewhere.
Oh.
Is it because it can't happen?
It has a boundary you can pass, which means it's skewed one direction.
Right.
No, it can't be.
So like have a lower point for
Yep, so standard deviation, matter what.
Did you want to say yes or something? Just like, no, it can't be too much, it can't be.
That's gonna be.
The standard deviation.
No, I just don't like hearing about
Like the point.
like chemistry stuff, like, oh. I
Probably
heard
not.
yeah, but like, I don't like care all that.
Yeah,
It's
it's like,
just that.
Right, so we're taking
Deviation.
the size of 100.
Yeah, I know, but I know.
That's a big sample size.
That's not what we're talking about.
Yeah,
Why
right.
about this can't be negative? Standard deviation, you say it's large compared to me.
Yeah, what's that to do with it?
That gives us a clue that there's a boundary that can pass.
I don't know.
This from the, we did in class, I did over meeting. Remember how, when you multiply the standard deviation by 2, when you went to the left, if you subtract it, you get a negative number. That's just skewed to the right. It's basically the same thing as this, because you can't have a negative part per million for the error test. So I'm just saying, because standard deviation is higher per deviation, that means it's probably skewed one direction, which therefore means that the fine boundary you can't go past that, then say, we get a negative. Error test, personally.
Or is largely skewed the larger,
You can say whatever you want.
but I think that, I actually want the.
I don't know. So we don't think
Whatever observations are. You know that they're there on the x-axis, you don't know what the y-axis is. It's just asking about individual measurements. So for that, sample size doesn't come into it. There you're just talking about sample size one, like individual measurements. 374. So. And then it's like big graph. And like says that number is so big. No, not if each dot is one person. This is our, if each dot is one person, then it could be normal, rights to be one. The normal distribution really comes into it. Each dot is the mean of a large sample. Oh. Yes. Yeah. Yes.
Standard deviation is mean divided by square root of 9.
Oh, nine.
Is it 9? No, it's
Oh, no, that's one.
yeah, it's square root of 9.
Yeah, because it's right.
Well, I don't remember these, but that's just which basically is
Yeah,
the
so
same thing.
the mean of the population should match. It's showing you
You got the top graphs, right?
which side of the cutoff you want to have that. So this is here. That one, and she has 5%. So you want, did you do that on your left? No. 5%. Here, we want.
What was the reason for the first one again? I already forgot.
Right.
Well, why was he
Well, I just based on this.
like being smaller or bigger?
So you can do that. So you can do one.
Well, I already know that. I already know it's smaller. Smaller.
I think it's the wrong number.
Everyone, it talks about, like, your calculator just doesn't, it said that, like, the mean of the sample population. Population, that's because you cited. But you really, and then you want your text to make a standard deviation. So my, but that's right, the only thing.
So the mean would be 35. Yeah, the larger one is the smallest. It's like 25% of the large or sample size. It's like higher than more standard deviation. Okay. Nice. So.
We don't need that for this problem because. Any questions on the thing? Like standard deviation equals the standard.
Oh, true. As long as we have this one.
Oh, no. So one important thing here is that the population is referring to individual observations. So you can sort of think of that as samples of size. So if anything is going to be skewed, the population is going to be the most sensitive.
When it says the population, it means individual observations in the population.
Oh, so this is X.
Right.
And then this is something S.
Yep, exactly.
Yeah.
That is what these problems are for, to explain different technology.
How would you know what it's actually talking about?
Yeah. So when we say something like the mean of different populations. Then, yeah.
We want to know if it's.
You're welcome. Any questions?
Was that just the same thing?
So that's an interesting perspective, but it's not what this question is trying to get at. So we have no. This is like this thing about it. It's infinity.
For what?
They're giving
Oh,
their
I
merch.
literally drove all the way down to my phone on the way back. I see the word open sign. Oh, right. They were open. I like looked up online and she didn't like say they're open. Yeah. So I really said it's full lady in there. So I like so we would up on there and everything. Check my calls, like I saw right on there. Of course, on my back, I drive by the sign that says we're open.
Oh, yeah, we're open.
Yeah. On a bike over there. So I'm taking-
Rocky bike.
Oh,
How do you bike?
that just means you need to. That's what it means to bike.
Oh,
So you don't take it. That's what I'm here for. I like that show you the perspective of the thing.
I bike there and then I went for bike ride last night. Bike over. Oh, I like bike to go there, but I was biking, I have to pass one, so then I stopped.
Oh, well, I guess. When you don't know.
Yeah.
All right, so let's talk about this. For problem one, which distribution represents the population? Let's do hold up fingers, 1 for A, 2 for B, 3 for C. So hold up fingers for the population. 2, yes. So what's the thinking here? Why is graph B the population? It's the most skewed, yeah. So we can think about the population as being made up of a whole bunch of individual observations that we're not taking any means here yet. We're just measuring individual people, perhaps, and graphing their values. So we don't have a large sample size for the central limit theorem to kick in and have it be normally distributed. We just have samples of size 1. So if anything is going to be skewed, the population, so the individual observations, are going to be the most skewed. All right, so graph B is the population. And then between graphs A and C, which one is the sample mean of samples of size 30? 1 for A, 3 for C? Yeah, that's graph A. Why is it graph A? Mary?
Because as the population gets larger, the standard deviation is smaller, and graph C has a smaller standard deviation than graph A.
Right. So looking at the horizontal spread on the axis, graph C has a smaller standard deviation than graph A does. So graph C must be the sample means of larger samples. So graph C is means of samples of size 100. Graph A is means of samples of size 30. So it seemed like people were pretty okay with problem 2A. Does anybody want to talk about that one? All right, let's skip down to 3. So we want to find the number of pages that would allow a student to attend the pizza party. So to be in the top 1% of number of pages read. What calculator function are we going to use for this? So Normalcdf would let us find the probability that a particular student would have more than 300 pages read. So that would be if we were given a number of pages and we wanted to find what percent of students were above that. Here, it's the opposite. We're being given the percent and we want to know what cutoff for the number of pages will give us that percent. So instead of Normalcdf, which other function do we want? Right?
Inverse.
Yeah. All right. So this is inverse norm. And the way you're going to do this might differ slightly depending on which kind of calculator you have. So the mean is 200. The standard deviation is 75. And then if your calculator lets you put in left, right, or center, probably the easiest thing to do is say, we want the top 1%. So we want to find this X value so that 1% is above that, is in the top part of the distribution. So in other words, to the right. So if your calculator lets you, you can do to the right, I want 1%. What do you need to do if your calculator doesn't let you do that? Yeah, then you would use 99% as, oh, sorry, this should be a decimal. One. Because then your calculator by default uses the probability that it wants to the left. So using the complement rule, if 1% of kids are to the right of this X value, then 100% minus 1% or 99%, are to the left. So these two methods will give you the same answer. You just type them in a little bit differently depending on what calculator you have. Questions about this one? All right. And then for number 4, do you think that the normal distribution is likely to be a good model for the carbon monoxide concentration of individual tests of air? Let's do thumbs up for yes, thumbs down for no. Yeah, why is it thumbs down? Nettie? What's that? Yeah, these aren't averages. These are individual observations. So the individual data points, like if we made a dot plot, each dot would be one test of air. So that could have any distribution. It could be normal. It could be skewed either right or left. But in this case, we have a similar situation to the salary problem that we talked about at the start of class. We know that the carbon monoxide concentration can't be less than 0. And the standard deviation is large compared to the mean. So the empirical rule would tell us if the distribution were approximately normal, you'd have 2.5% of your tests of air would have a negative concentration of carbon monoxide, and that's not possible. So it must be that the empirical rule doesn't apply. It must be that it's not normally distributed. It's probably right skewed. Then once we get down to part B, now we're taking the mean of samples of size 100. So this probably does have an approximately normal distribution. Because now we are talking about the means of a large number of samples. What's the mean gonna be? Yeah, it's gonna be the same as the mean in the population. So 12 parts per million. And what's the standard deviation gonna be? Is it gonna be 9? No, what is it gonna be? Yeah, it's gonna be 9 divided by the square root of the sample sizes that we're taking the average of. So 9 divided by the square root of 100, which is 9 divided by 10, so 0.9. All right, thank you all for your good work today. I will see you tomorrow for hypothesis tests based on the normal distribution.
Why?
What's that? Why? Because you don't always have access to the one mean aspect.
You know what our lab example is? Next Friday.
Yeah.
That's so awesome.
Yeah, she's gonna average so your grade for the test will be average.
So awesome.
Yes, but it's open.
Oh. Wait, what's the deadline for that? Okay, so that's-
So like the original, was that like the sample, like, just like from the population? Because it's not based, and so like, yes, it's part of the central limit theorem, but you don't actually like, it could be large and distributed. Because standard deviation, so the ones that seem to the cabinet things like, like empirical, that's gonna be right.
Okay. So the
Yeah.
deviation.
Here's an open boundary. Those are often left skew distributions. And if the standard deviation is large relative to, I guess, the difference between the mean and the upper boundary, that would be what evidence says that's. Thank you very much.
It's like this is the big population. And we took a small sample. We're getting to standard deviation.
We're taking many samples of size 100.
Oh, okay.
And for each sample of size 100, we're taking the average. So this is the standard deviation of the averages. Oh, don't say that. Fun is fun.
It is, but it's not something like so I always end up with a lot harder. And if it hurts, then I just say stretching and stretching is a good thing.
Okay, that's a good way to think about it.
I'm the kind of person who apparently likes pain to the point that if I were to